Hello, I'm here to show my project 1 for fundamentals of aerodynamics. I'll be going over the inviscid portion of the project. So here to start off, we have our geometry, which I'll load. Here we have a cylinder. It's one diameter across, as kind of stated in the description for the project. The control area around it is 50 by 50 meters surrounding the cylinder. So that's about it. For the design modeling, I just did the sketching and all that for it as he kind of specified in the tutorial. So that's that for the modeling. Close out of that. Next we have the meshing. Here for meshing, you can see the cylinder again. Click on mesh. It'll load up. Here it is. I chose 0.12 for my element size to try and get more accurate numbers because there's more nodes than like 0.15 or 0.2. I used the triangles method, kind of did the edge sizing and the inflation, just how he described it in the tutorial video. So it's pretty similar to that in all aspects except for my element size, which I made smaller. So that should be about it for the meshing. Next we have the setup, and this is for, actually, no, I'll do the solution since it'll already have all of my plots. But I will run through my setup as well in the solution section. Okay, so for inviscid, I mean, in the general, it's just steady, all that. Then for the model, I just have inviscid on. And for the other cases, for instance, laminar, I would change it to laminar. For turbulent, I'd change it to the, I don't know exactly how to pronounce this, but the one equation model. So that was about it for the modeling portion. Next for materials. For the air, it's just constant with constant one with the inviscid. However, for the turbulent and laminar cases, I did have to change my density to different numbers in order to obtain the Reynolds numbers that were necessary for those cases. So that density will be different because I changed that in it as opposed to the viscosity. And then for our boundary, you just go to inlet. I set it to 10 meters per second as specified. Looking at the cylinder wall. Here, you can't really do much with it because it's stationary in this case. However, in the future cases, I did have to change it to moving and rotating with the negative 20 radians per second and the negative 40 radians per second cases. As for methods, I kept it as he did it in the tutorial, was simple for the scheme, least squares cell base for gradient, presto for pressure, and second order upwind for momentum. I kept this the same for all of my different run throughs for each case. As for controls, I kind of just left it like this. I didn't change anything. Same for report definitions. Same for monitors. I just kept the residual at 0.001. For the initialization, I just ran it 35 times as the same that he did in his tutorial. For the run calculation, I ran 1,000 iterations, and that seemed to be enough to get a pretty good contour and just other numbers. And actually onto contours, after running my numbers, put in pressure coefficient for all of these contour lines, and then compute and display. As you can see, I got a very similar contour line to how it should look. I imagine it's very symmetrical. You can see your pressure is 1 in this red area, and it's pretty much a -3 in the dark blue area. And then for velocity, magnitude, compute, display, kind of the same thing. It's around 20 on top and bottom, and much lower at the very front, as it should be. And then onto the X and Y plots. Looking at our pressure coefficient and the direction vector. Show that plot. As you can see, it starts at 1, goes down to -3, as discussed in class many times. So that's looking pretty good. Then for velocity, magnitude, kind of same deal. Starts at 0, goes up to 20, goes back down to 0.5, kind of as specified. That's it for the XY plots. And again, it's different for each case, but I kind of did the exact same thing. I just, changed it from inviscid to laminar, stationary laminar to rotating, or to turbulent, or whatever was needed for that case. Then for report, it's just as he specified. You go to the forces in the report. If we want to find your drag, you put 1 in X and 0 in Y. Print, you can see it down here at the bottom of our screen. Have that for that. Then for Y, to find your lift, you'll change Y to 1 and X to 0. Print it, and this should be your lift coefficient. So that was your drag and your lift coefficients. That's about all that was asked for in the well, not asked for, but that was about all that was shown for steps wise in the tutorial, and it kind of covered just about everything I needed to do. I did save the plots to my files and then put them into Excel. So that's pretty much like how I did that for those. And I just made a graph in Excel for them. So that's how I did that. Aside from that, the contour, you'll be able to see really all I did was, all I did was screenshot it and then put it into my report. It's kind of the clearest picture I could get. And then for the very last step, it'll load. you just click on results, and this is to get our streamline, which is one of the last things asked for. And it'll load up. Full load, there we go. And all I did for this was I created a streamline. I clicked on it. In the tutorial, it shows a surface streamline, but for whatever reason, my computer would not load that no matter how long I waited, and it would kind of crash the program. So I tried the 3D streamline with the velocity inlet, and it looks like it represents it pretty well. So that's what I did for that. I put the number of points at 400, kind of like you did in the video, and I took a screenshot of this and put it in my report, and that's how I did it for each case for the project. But that should be about it. You can see here, I mean, I have a case for each, you know, laminar. Well, I put non-transient because I couldn't get the graph looking right at first, so I tried transient, but that's the only one I have now. So it's just, yeah. But then I have laminar rotation at 20 and 40 radians per second, respectively. And then I have my turbulent right here. So that should be about it.